thanks for coming this morning. Thanks to Nuffield for inviting me, and thanks to the conference for hosting me as well. So, I call myself a sports engineer. Essentially, I trained as a mechanical engineer, but really what we do is we try to understand the fundamental physics of what's happening in the world of sport, and then we use that to kind of innovate or create technologies, and we sell these things to companies or to national teams, and that's really the nature of the business. So we're quite a I'd say a leading centre for this. In fact, something I think the UK can be really proud of in this sort of field. Talking about sports technology, it's something certainly an area where we lead the world. There's ourselves at Sheffield Hallam, colleagues at the University of Loughborough, and together we really sort of dominate this world. And we work with lots of the big multinational companies, so your Nikes and your Adidas. They don't do their research in Germany and in America, or they do some of it there, but they come to the UK to do it, so we do a lot of their work for them. And we work in a lot of different sports. So obviously this is typical example sort of work we'll do with cycling, Planet X, sort of a Sheffield-based bike company. We do a lot of work in the more technology-heavy sports. So, tennis, for example, has gone through a major sort of revolution in terms of the materials that are used in rackets, and that sort of innovation and development process is still going on. So this is work we do with, say, for instance, Prince tennis rackets based in Italy. We do a lot of work in the football, for instance, looking at measurement devices, how we can track the motion of balls and players, how we can look at say the traction of footwear, how we can understand how players get injured, perhaps because of the equipment they're wearing, or how we can make players use different equipment to try to reduce injury. That's sort of a key part of it as well. And I guess what we do is we kind of we borrow almost other people's technologies. The sports industry isn't really big enough to actually really create new platforms of technology. So what we do is we borrow sort of ideas and concepts that have maybe been proved, say, from the automotive industry, from aerospace, and from other industries, and sort of suck in that knowledge and then apply it to our world of sports. So, for instance, three-dimensional laser scanning is something we do loads of now. We're scanning full athletes and sort of fitting bits of equipment specifically to those athletes. But these are technologies which are often proved in other industries, and we're sort of borrowing off them. And we've done some great work. I sort of mentioned some of the more kind of commercially ended sort of stuff about selling rackets and boots. But obviously we're really involved in the push for sort of national pride and national success at the Olympics as well. We've been working with, for instance, British cycling for many years, really back into sort of 2001. I think we started working with them, developing the bike that's ridden by the British team, and other aspects, helmets, and some of the training equipment they use, and some of the measurement devices that we're putting on the bikes to say, measure the power output of Chris Hoy or whatever it is. So we work with these teams through UK Sport. So UK Sport are the big overarching body that look after sort of elite performance for UK athletes, and effectively they fund us to work with teams, and we're working with I think 14 different Olympic teams in the build-up to this summer's games, and we're actually already working on the next Winter Olympics, and looking forward to the Commonwealth Games in Glasgow as well. So 2012 isn't the end point. We would have been doing this if it wasn't for 2012 happening, and we'll carry on doing it afterwards. So this summer is fantastic. It's a high point for us, but it's not the end of the road. It's really just sort of part of our journey, really. And so, classic examples. A lot of the stuff we do is around things like aerodynamics, material science, that sort of thing. So here we're sort of redesigning aspects of the bike, and equally we did this very successfully with Amy Williams and the skeleton bobsleigh, who got the first gold medal, the first individual gold medal in the Winter Olympics. So we helped with the sled development with other partners, BAE Systems and University of Southampton as well. But again, looking at really what we're trying to do here is we're trying to shave off hundredths of seconds by subtle changes in sort of equipment design. We have to, it's a tricky game because we have to sort of play within the rules. The rules sort of outline and describe what we can and can't do. But you know, when you can make small changes, sometimes that can mean the difference between success and failure. Although I have to say, and it's something that I'm always very sort of passionate about, is that the athlete is still in control of this. And particularly if you look at the say the British cycling, take an athlete like Bradley Wiggins on the velodrome, he's winning by seconds on that track. And as engineers, we can make differences of maybe hundreds of seconds. And so those athletes are still winning. But, you know, if push comes to shove, we might just give them that tiny bit of edge. But I think in the vast majority of cases, the athletes are still in charge. A lot of work in disability sport as well. I'll come on to that later. So that's kind of us and who we are. We're a pretty reasonably sized research centre. There's about sort of 15 to 20 sort of postdoc research staff and academics, about 15 odd PhD students, and sort of 15 to 20 master's students as well. And so we live and live and breathe this work. We also do a lot of public engagement work, or work with schools, work with adult audiences, museum sectors, and all sorts of things. And I'll come on to that later. But I thought what I could do for you today is just give you a bit of a few little insights, and maybe to a few different sports, and tell you a bit about how this relationship between science and sport, and maybe just to give you a few ideas of things that you might be able to sort of take away and develop for yourselves, really. So I'm going to whiz through some classic sort of Olympic disciplines and delve into a bit of the physics and the science behind what's going on here, and tell a few stories. So the first one is the javelin, sort of the classic sort of hang on a sec, I'm going to have to put the volume up here. So obviously javelin being one of the classic Olympic disciplines on the field. That's Jan Zalesny, you might recognise him. He's the current world record holder. And of course Steve Backley, his great rival in the 1990s. A fantastic period for this sport, really. Okay, so what is the relationship between science and something as simple, as primitive as throwing a spear? But of course there's an awful lot. Because there's a lot more going on than simply throwing a spear. The javelin is an innately an aerodynamic object, and it's not thrown. It flies. It doesn't just get thrown. It actually flies through the air. I'll show you why. So there's a lot of aerodynamics going on when the javelin gets thrown. So the javelin's quite interesting because it's gone through quite a significant change in actually the design of the javelin, due to a rule change, which I'll explain. So this is prior to 1984. The javelin would, essentially, you throw the javelin and it gets thrown at a certain sort of direction, its velocity. Obviously we've got its weight pulling it down. We've got some aerodynamic forces pulling that javelin backwards through the air. So obviously javelins aren't being thrown in a vacuum. We have to deal with air, and that air creates drag, and it also creates lift. But the interesting thing is that if you imagine you've got the mass of the javelin pulls down here, okay, but the aerodynamic forces, almost what we call the centre of pressure, that doesn't act in the same place as the weight. And that means that we get what we call a couple. Effectively, that creates a pitching moment which rocks the javelin backwards. So as the javelin's flying through the air, it literally gets rotated backwards because of where the aerodynamic forces are acting. And that creates a very sort of... it's actually very, very advantageous if you want to create a long distance, because what it does is it creates a very large angle of attack. That is the difference between the way the direction the javelin's going in and the direction it's pointing. So you actually, it opens up almost like the belly of the javelin to the oncoming airflow, and that generates more and more lift. And some athletes have been really good at exploiting this, because that additional lift allows the javelin to be thrown further. So East Germany, Jack American Alcatraz, world record by over 16 feet.
342 feet, 10 inches, watch where it lands, just inside the stadium. After this, the weight of the javelin will should be increased. The stadium are not picking up.
That's right. So if you can throw these things right, if you can really understand how this aerodynamics works, you can literally start to throw these javelins outside of the stadium, which has a very serious health and safety risk. You've got runners coming around here. The javelins are thrown here. They're not really being thrown out of the stadium. But so that's away on from East Germany, and he threw a javelin 104 metres, and that was literally landing in the pole vaulting arena. And you get multiple sports happening at the same time. Okay, inside the stadium. So there's a very serious limitation. So what do? You've got two options. You either take the javelin outside of the stadium, or you change the way that the javelins are shaped. And just in that little video clip, they said, surely we're going to have to increase the mass of the javelin. Well, you can't really do that, because javelin throwers already get horrendous back injuries because of the loads they put themselves through. You make them throw something heavier, they're going to be more likely to get more injured. So they didn't want to do that. What they did is a very subtle change, and it's actually just all about the aerodynamics of this javelin. So all they did was just didn't change the overall mass of the javelin, just moved the balance point, the centre of gravity, slightly further forward. That meant that the centre of pressure, the aerodynamic forces, were then behind that centre of mass, which meant that when the javelin's flying through the air, it would always rock forwards. It would always close down its angle of attack, and you therefore generate less lift, and the javelin would get thrown less far. It had another really good benefit as well. Another rule in the javelin has to land tip first. It's for very good reasons. You want to be able to measure where the javelin lands, and if it just lands on its belly and skids along, it's not very easy to judge where it's actually hitting the ground. So it wants to land tip first, and this actually allows for more legal throws. Particularly prior to 1984, almost like half of all the throws were actually illegal throws because they were landing tail first. So this is a very neat little change, some interesting physics going on to sort of really reduce those distances and sort of make the game easier to regulate. This is some good data here. I'm going to talk you through this. So this is actually quite a good data set. But you can get data sets like this from loads of different websites, the Olympic websites, the IAAF websites, all sorts of athletics, statistics kind of sites. You can get great data. This is actually a bit better than that. Each data point represents the top 25 performances in each year for the men's javelin. And for the men's javelin and for the 10,000 metres running. So why am I trying to compare these things? Well, what we've actually done is we've normalised this data. So we're not talking about distances thrown or the time to run the 10,000 metres. We talk about it's what we call a performance index. It's actually a ratio of energy used to achieve this feat. And we use a baseline from 1948. And what it says is basically, in 1950, javelins were being thrown sort of, about 2% further than they were, or throwers used 2% more energy to throw than they did in 1948. And it means we can compare different sports to each other on the same axis. It's very, very useful. And if you take the case of the 10,000 metres, what we see is you've got, from 1948, we see quite a sort of steady, sort of linear kind of improvement, quite a levelling off, actually, in the mid-1970s, about 20% improvement from 1948, sort of a generally sort of static sort of progression, then actually a pickup sort of in the late 1990s, and that's actually the influx of East African runners who have really started to dominate and really push that sport forward. But at the same time, you can then compare, and I guess we would argue that the 10,000 metres is actually a very low-tech event. No one's ever made a go faster running shoe. It can't be done. And in fact, even changing from, say, cinder to tartan running tracks had very little sort of implication for the times that runners were running. And so that's sort of like the low-tech baseline. Now, we always see improvement in human performance, and that's because of all sorts of things, globalization, the subtle changes in physiology, just generally sort of the competitiveness and professionalization of sport, that drives up results. And we'd see that's like our baseline improvement. And anything above and beyond that would be an outside intervention, such as a technology. So if you compare the two to each other, you see that they're sort of side by side, the javelin 10,000 metres. In sort of mid-1950s, the javelin deviates, and it's because the javelin was made hollow. It was actually made out of aluminium, and that increased the surface area, which meant it had more aerodynamic lift, so it could be thrown further. And that sort of carries on pretty much on a level, side by side, until we get this rule change in mid-1980s, and the performances drop right back down to basically the 10,000 metres. They start creeping up above again. There was a second rule change in sort of 1992 to do with these sort of turbulators on the tips of the javelin. They were removed, and again we're back down to this baseline, and they go side by side nicely right until this sort of influx of East African runners. I think it's quite a neat way to see there are these overall trends through human performance, and when you introduce or take away a piece of technology, you can really see it in the data. And we've been doing this with pretty much every sport you can imagine, trying to look for, as engineers, we think we make big differences. But do we really see it in the data? And we're looking at lots of different sports. Can we really see the impact of these changes? So really nice bit of data. And so a lot of this data is freely available. I think it's really, really powerful to use this. So I'm going to talk about another sport. I guess another sport quite close to my heart. I do a lot of triathlon. So that's really sort of my thing. So I spent a lot of time in pools, swimming. And swimming is innately a very, very technical sport. You've got a huge amount of technique. Now, I'd call that a technology. Technology is actually, sort of the official definition is know-how, knowledge to do something. It can be an idea as much as a practical thing like this recorder here. So knowledge of how to swim is a key thing. Knowledge and technique is absolutely critical when it comes to swimming. However, there's been some other technologies going on as well. Things like swimsuit technology has been really sort of in the media for a long time. Certainly since the millennium, for the last 10 years, swimsuit technology has really been sort of a big story in swimming. But it goes back further than that. And really, the 1970s, this is Mark Spitz, one of my heroes. You can see him there. He's wearing his elastane trunks. Before this, swimming trunks were not too far before this. They're actually made out of wool, and they dissolve an awful lot of water. And of course, that would slow the swimmers down. And this was a key innovation. Also, prior to the 1970s, swimming goggles weren't being used. And that would limit the amount of time that swimmers could spend in the water, because literally they'd get chlorine in their eyes, they'd get chlorine rash in their eyes, and that would mean they could have trained for 2 hours or 3 hours. If you wear goggles, you can train for 4 hours in the pool, and we see this sort of an improvement in performance as a result of that. But it was really in 2000, the Sydney Olympics, where things really started getting interesting in the world of swimming, because we had this idea of like a full-body swimsuit that could somehow reduce the drag that's acting on the swimmer. And it was a stroke of sort of marketing genius. Speedo called it the Sharkskin suit. So what is it all about? Well, it's a nice idea. It gives us this idea of biomimetics. We look to nature for sort of these elegant solutions that have been found through evolution, and can we learn something from them? So if you look to how do fish swim so fast? Well, they rely on a number of different techniques. They've got all sorts of fins and so forth. Well, you can't really do that within the rules of swimming. Although actually now there is a new discipline called fin swimming now, which is very popular in South America, where they use fins to swim. It's like a deviation off the branch of conventional swimming. But you could think about doing something with fish slime. So maybe we could have some sort of slime that would be excreted out of this garment to reduce the drag. This is what happens that fish do. Maybe you could blow bubbles. A lot of seabirds blow bubbles when they're swimming, and we think it basically sort of disrupts the boundary layer, it kind of affects the fluid mechanics, and we think it actually reduces the skin friction and the drag. I guess the one that you latch onto is the Sharkskin. So Sharkskin obviously is very, very rough. It's actually used as a tool for building. You can sand wood with Sharkskin. It's so sharp and abrasive. And it has these little things called dermal denticles, little sort of very sharp ridges. And essentially, what they do is they sort of align the turbulence as the fluid moves over an object, and it can reduce the skin friction. And they use it on some ships, certainly use it on missile design for sort of defence and so forth. So it's actually a proven idea. It does have an effect. It's slightly mysterious how it exactly works. Our understanding of fluid mechanics isn't quite at the level where we can really model it precisely, but it certainly does seem to have some effect. So the question is, can you put this on a swimsuit? Which of course is what they tried to do. They wove a suit that had little ridges on it, little aspects of the textile was designed to have this certain roughness. A lot of simulation was done. We did some of this. Where we basically, look at a swimmer going through the water, looking for the regions of high pressure and low pressure. Where are the high drag points? This allows us to make some design choices, maybe as where you put these rough sections. Where do you want to put these rough panels on the suit? And so we do sort of computer modelling, simulation type work, and that informs the design process. Great idea. However, it didn't work. It's slightly, from speed I wouldn't like me saying this, but it didn't work. We see no real improvement in the performance of swimmers by wearing this suit, not above and beyond what you'd expect to see in an Olympic year anyway. So it didn't really have any effect. It's a great marketing ploy, but it didn't really work. In fact, it was an altogether different technology which really set the world alight. And it took until 2008 for this to happen. So they sort of spent 8 years messing around with this Sharkskin business, but it didn't really get anywhere. And they moved to an entirely different technology. It was a technology that used a polymer, polyurethane, and this is it's quite interesting. It's a hydrophobic material. That means that it sort of literally repels water. So when a water droplet sort of lands on a hydrophobic material, rather than the droplet dispersing, it actually holds its shape. And it's to do with sort of the microscopic geometry of that surface, just keeps the water droplet formed as a sort of hemisphere, as it were. And that somehow reduces the skin friction. So polyurethane has this property. So you make a suit with these polyurethane panels on it. It was a very tight suit, it was a very lightweight suit, and it was great. We've got huge records, 79 new world records being broken in 2008. The Beijing pool was set alight. World records being broken, and it was sort of this fantastic festival. Thinking, wow, this sport's really moving on some here. It was with a little bit of controversy as well. Some people were starting to then question, what's going on here? These suits, they're really changing the nature of this sport quite dramatically. Is this what we want? And the next year, things really sort of stepped up a gear. Rather than just using sort of little panels of this material, polyurethane, full body suits were being made out of it. So a fully synthetic suit, no textile in it whatsoever. Other companies got involved. Jacked were really, really successful with this. And in the FINA World Championships, which is like a 5-day event, they got 20 new world records being set. And it was, people started to realise something quite dramatic is happening to the world of swimming because of these suits. People were saying there's a step too far. People were squeezing themselves into suits so tight they were literally sort of bursting out of them, quite literally. People were doing all sorts of crazy things that they thought that, one suit is good, therefore I'm going to wear 2 or I'm going to wear 3 suits, all sorts of ideas. There were questions around buoyancy. So are these suits actually buoyant? Are they really artificially floating the athletes? What they might be doing? They might be trapping air. They're so tight. They're trapping air pockets and providing some level of buoyancy. FINA, this is being recorded, so what should I say? FINA made a complete hash of this. They really struggled to react to this. in a sort of a sensitive, appropriate way. They were very reactionary. They made loads of different rule changes very, very quickly. They came up with all sorts of tests like, are these suits, do they provide buoyancy? Oh no, we'll put them in the water, and if they float, they're buoyant. If they sink, they're not. This was the level of their sort of understanding of what was going on. Really, really poor. And basically, they banned them. And it was largely driven by the media. You had athletes like Rebecca Adlington saying, damning the controversial suits as a form of technological doping. She says, I would never in a million years take a drug to help me, so why would I wear a suit just to improve my performance? This idea that this is akin to taking a drug, the great scourge of sport. Slightly hypocritical, I have to say, Adlington there wearing her fully polyurethane suit, but nonetheless, this is what athletes can do. And the media really latched onto this, and it became a great evil, and they were banned. So now we are not allowed to use any of this technology. So from 2010, all of this stuff has been totally revoked. You can't wear a full body suit. If you're male, it can't come above the waist and not below the knee. Female, kind of similar, but it can't come beyond the shoulders and not below the knee. But importantly, it has to be a woven fabric. It has to be a textile. So you can't use polyurethane. You can understand why they did it, but at the same time, this was quite an interesting, exciting advance that we didn't really fully understand, actually, and now it's been taken back. So I'm slightly, as a technologist, this wasn't a good day for me. If you look at the performance data, again, this is really interesting. So this is basically the percentage difference from a baseline of 2006. In 2007, we see this gradual improvement, sort of 1% improvement. 2008 was when these first polyurethanes first came in. Massive improvements, about a 3% improvement. This is all strokes, all distances. Massive data set, absolutely enormous data set. And then in 2009, we saw basically a 5% improvement on 2006. 2010, this is when the suits were taken away, and we're right back down to basically where we were in 2007. And we've done a lot of work on this, and we don't think that the world records that were set during this enhanced period are going to be broken for many, many decades. The level of performance, you always see this gradual improvement, but the performances are tailing off because they always asymptote. We've got a big spike in it. It's been very, very hard to get back to the levels that were set in that period. And that has implications because as we're consumers of sport and we like to see progress, we like to see records fall, and what drives attention and column inches and all this stuff. And you take that away, and potentially that can have quite damaging implications for the popularity of a sport like swimming, unless they make another change, like they could either allow the swimming suits to come back, or they could actually remove these records from the history books, or asterisk them in some way, so that new records could be set. There's only one record that's been set since 2010, and that was in a very long-distance event where these suits have very little impact. Compare that to 79 records being broken in 1 year. In 2009. So technology has implications. I think that's a bit of a message there. So I guess the question is, well, where do you go from here? I was a bit of a sort of a negative role about what could, this great problem that's happened to swimming. Well, we can still do things. There's sort of a number of different ways you can look at things. So we work a lot with British Swimming, and we've been developing various measurement devices, looking at how we can map, say, the power profile of swimmers, look at technique. Effectively what we're doing is we're doing biomechanical measurements underwater, looking at sort of technique development and so forth, because it's such a technical sport, you can make sort of improvements in that way. You can also look at, the technique of the tumble term and the glide and so forth, and you can start making improvements there. This is an interesting work, though. This is actually looking at what are the physics of propulsion underwater, to try to understand and model how propulsion actually happens when you're swimming. So this is again sort of the cutting edge of fluid mechanics, really. Work we're doing and trying to understand how we can model how this propulsion happens. Quite formative, really. Basically, what it will tell us is maybe what the athlete's doing already. But if we can understand the physics of it, it might open new doors, new avenues, new opportunities. And just explain it. So, all right, so on to the final sport I want to talk about. Again, something that's probably quite... It's wrapped up in a whole load of sort of controversy and emotion, and it's the issue of course, disabled runners wanting to compete against non-disabled runners. No prizes for guessing whose legs they are. This guy is going to be the pin-up boy of 2012. This is going to be a huge story. This already, there's sort of adverts with him all over. Of course, it's Oscar Pistorius, the so-called Blade Runner, and we'll come on to him in a bit. But I guess, sorry, apologies. I guess when you're looking at say prostheses for running, or for generally for sort of mobility, the general sort of design specification is that they should mimic the performance of the remaining leg. It's very rare for an athlete or an individual actually to be a bilateral amputee. That's to say, to have both an amputation in both legs. It's much more common to be a single leg amputee, and in which case the leg that's had the amputation, you have a prosthetic on that leg that effectively mimics sort of the flesh and bone of the remaining leg. There's no real point in having some sort of turbocharged prosthesis on one side if you can't match it on the other side. You'd have a very unbalanced gait, and it wouldn't work at all. However, if you're a bilateral amputee, you don't really have to worry about such things because you can retain the symmetry on both sides. You can do all sorts of things. You can change your height if you want to. You can be 5'10" one day, you can be 6'5" the next. You can have an optimum height for the 400 metres, an optimum height for the 100 metres, optimum height for the high jump. You can do whatever you like. Of course, this is Oscar Pistorius. He's been, what an amazing athlete. He's dominated the world of disability sport for sort of 8 years or more. Won literally everything there is to win many times, and quite understandably he's now set his sights on wanting to run directly against non-disabled athletes. There's a long story to this. Essentially what happened was, well, I'll tell you what happened. I think I've got slides to explain what happened. I guess the question around Oscar Pistorius is are these devices, are they just enabling him to run, or are they enhancing his ability to run? That's the question, and it's been a pretty charged debate so far. I've actually received hate mail because I've been writing about this, because it really is a hot topic. But it comes down to some basic science, really. I saw Oscar Pistorius run in Sheffield in, I don't think exactly when it is, I think it's 2006. It was his first time he was allowed to run in a IAAF sanctioned event, and he ran in Rome sort of the following week, and the IAAF, the International Amateur Athletics Federation, they sort of did a bit of a study on him to understand how he was moving, how he was running. And basically what they found was that if you look at how all elite 400 metres run, it looks a bit like this. This is the time for each 100 metre stage of the race. So the first 100 metres, they do it in about 11 seconds, do the second 100 metres in about 10 seconds, third one, sort of back to 11-ish, and then the final leg, that final 100 metres to the 400 metres, is always considerably slower. It says literally sort of human physiology, you cannot move oxygen to your muscles fast enough, and therefore you use the sort of anaerobic energy system, which means you build up lactate acid, which means you have to slow down. You just cannot get over this. You have to slow. And this is what all elite 400 metres runners do. Another sort of way to describe that is if you say, take the difference between the first 200 metres, the running time, and the second 200 metres, what's the time difference between those, sort of the first half and the second half of the race? These are all elite 400 metre runners, and the second half of the race is sort of 2 to 3 seconds slower than the first half, apart from one athlete here who runs the second half faster, and that's Oscar Pistorius. So he speeds up as he goes along, and his final leg is the fastest 100 metres that anyone ever runs. In the 400 metres, you know, he's going faster than anybody. Based on that, the IAAF banned him, essentially. They said, hang on, whoa, there's something very, very different going on here. This isn't running, okay? This isn't what we call running. So something's different. So they banned him, and they did some studies. Essentially, what those studies did was they looked at, I guess, two things, really. Firstly, the idea of how much oxygen is this athlete using when they're doing the 400 metres. So, you know, in sort of physiology terms, oxygen equals energy. The more oxygen you breathe, the more energy you're using. So if you measure the amount of oxygen uptake, you can basically look at the amount of energy usage. Another way to do it is, or the other side of it, is to actually look at the biomechanics. Look at the motion, look at the weight, the speed at which he can move his legs, look at the forces which he can generate when he hits the ground, so the more the physics side of things. And I guess what would happen is if you understand the biomechanics and the physics, that should match up with explaining what's happening to the physiological side. That's the effect. Okay, so what was found? Well, the first key thing really is that if you look at this data is this blue line looks at how much oxygen. These are 14 Olympic or elite level 400 metre runners. So they've got some error bars on there because it's a bit of a difference. And this is the uptake of Oscar Pistorius, considerably lower. So this is the time over that sort of race, and you can see that Oscar uses considerably less oxygen, about 30% less oxygen than another runner. So that's a big finding. They based on this, they banned him and said, no, you cannot run. And it was for a number of different reasons. It is quite a complicated story, and it's not massively clear-cut, it has to be said. The first thing to say is when he runs, because his legs are so light, okay, he's got a carbon fibre blade which is lighter than an equivalent sort of set of muscle and bone, he can relocate his legs much faster. So the frequency of his stride is much, much quicker than any other runner ever. That has certain advantages. He does have other disadvantages as well, though. One thing he certainly can't do very well is when he... if you consider running is essentially a series of jumps, okay, vertical jumps, really, and certainly if you look at how high someone can jump vertically, it's a very good indicator of how fast they can sprint, or an extremely good indicator, which is why we do jump tests, to look at the sort of sporting talent. And he, because of his prosthesis, he cannot generate large ground reaction forces, which would create the jump. So he has a significant disadvantage there, but he can move his legs faster. However, he does have a major advantage, and that's to say that when he puts his foot down, a non-disabled runner, what happens is you get a large reaction force which pushes backwards, sort of in the opposite direction that you're travelling in, which slows you down. It's like a braking force every time your toe hits the ground, which is why you look for very fast feet, very short contacts to reduce that sort of impulse or the effect of that slowing your ground, slowing your movement. Because of the shape of the prosthesis, they're designed specifically to reduce these braking forces, and he experiences almost no braking force when he's running. There's another big thing as well, and that's to say that when you jump, I've got a bit of dodgy legs, so I'm not going to do it too much, but when you jump, okay, you don't bounce. The only way you bounce is to actively activate a muscle which uses oxygen, which uses energy, to create the rebound. If you jump, you just your body dampens out that impact. Oscar Pistorius doesn't. He physically bounces. He doesn't have to use energy to create that bounce. So he saves on that energy. He certainly loses in some areas, but he definitely gains in other areas. He certainly loses during the acceleration phase of the sprint, as he's setting off from the blocks, because he doesn't have a calf muscle. He finds it very hard to accelerate, but once he's up to speed, he can move faster than anybody else. And so you put that all together, and what happened was, I mean, I guess it's a story of science, really. It takes a while to get all this knowledge and understanding out, and there's debate. Papers get published, they get criticised. Other scientists come on board with different opinions. Effectively, what happened was, in the middle of this process, Oscar Pistorius took his case to the Court of Arbitration in Sport, and because there was some discourse within the scientific community, as there should be, the lawyers effectively exploited that, or the lawyers exploited that, and the Court of Arbitration in Sport said, no, you've got to run, you're allowed to run. And now he's made the qualifying time, so he's running. What do you think about that? I don't know. I think there's a very, very clear, now sort of almost unanimous, actually, agreement that has a significant advantage when he's running at speed. The degree to which he loses out in the acceleration phase is difficult, maybe perhaps to quantify. The other thing to say, the tests that were done on prostheses that were 2 years old. He's since had new prostheses, which have presumably been enhanced and developed. We haven't tested those. How are we going to ever know, whether he has an advantage or a disadvantage? But he's going to be running, and in many ways, a fantastic story for disability and overcoming these difficult circumstances he's been through. However, and I have to say this is what my fear, is that if he runs and he wins, will we have the same opinion? Or will we, if he runs and wins and beats British athletes, will we say, oh, it's all about those legs, he should never have been allowed to run? I don't think it's right, or it's not really... on one hand, you can't say, oh, I want you to take part, but I don't want you to win. You can't have that opinion. You're with it or you're against it. You can't have some halfway inclusive house. But I think it's a mess, essentially. So anyway, we'll see how that one pans out. But I guess it's another example of how, actually, and it obviously sort of highlighting in sport, but it could be any other discipline really. That science has implications, engineering has implications. When we change things, and as a society, it has implications for society. And I think that's a really fantastic way to engage people in topics. We've done so many sort of debates and events around the sort of the ethics of enhancement and what we think. Is there any difference between, designing a go faster bike to taking a banned drug? They're fantastic debates to have, really, and people get really drawn in, because particularly a subject like sport, where people have got very sort of passionate opinions and they care about it a lot. It's a fantastic context for doing this sort of stuff. So, I guess just. Oh dear, hang on a sec. So wrap that section up. I mean, I guess the Oscar Pistorius story is particularly intriguing because obviously it's got this context for the world of sport, but it has these wider societal issues as well. Really, about stuff that used to be science fiction, okay? This idea that in the future we might somehow integrate ourselves with technology in a very physical way to enhance our so-called natural normal abilities. Of course, that's already happening. Quite a lot of people in this room are wearing glasses, they're a prosthesis. We already integrate ourselves with technology all the time. But how far would it go? And, people have already elected, to remove functioning limbs, admittedly with limited functionality, and to replace them with biomechanical replacements that have an increased level of mobility or strength or control. It's already happening today. This stuff used to be the $1 million man kind of scenario. Well, actually, it's happening today, and where are we going to be in 20 years' time? Could be much further. And in 100 years' time, would you elect to have a limb removed for something that would be faster, stronger, better? You're not going to get arthritis, it's never going to wear out. How is this going to change sort of almost the nature of being human, and who's going to have access to it? you know, what's going to happen there about access and cost and money? Could be quite interesting, quite challenging stuff. Great, yeah. So obviously here the Decker arm, and then Hugh Hare with these are prostheses with their own energy source that can perform to very high levels. Quite exciting stuff, really. A lot of this has been driven by the military, by veterinary sort of funding for military veterans. So, thanks. Right, on to the next bit. I'll crack it. I've just got sort of my 10 minutes left. So, something I wanted to that's kind of a bit of an overview of maybe some interesting things that are happening in the world of sport. Loads of other stories you could tell. But really, I just thought I'd finish off by talking a bit about, I guess, some of the work that we do around trying to share these stories and trying to sort of just, you know, get some enthusiasm and engagement going in sort of physics and science and technology. Something we've been doing a lot of. Obviously, we've got a very busy year ahead of us. So a few sort of key projects for you to be aware of. We're about to start the Institute of Physics Schools lecture tour. So we're doing 74 odd dates around the country in schools. We're going to have a sort of show where we're going to talk about the physics of sport, this sort of thing. So that's going on this year. We always do lots of events as much as we can. Although I have to say, it's not our core business, so I have to be careful how much we do, because we've actually got to kind of write research papers and do the work. But we've just done a series of events at the Institute of Education. We've always done lots of stuff, lots of projects. Yorkshire Forward. I did a big sort of had a lab and a van tour. We went around every school in South Yorkshire. Did a schools lecture tour in South Yorkshire before that, and even in 2004 we did their schools lecture tour as well. We've done something crazy, something like 300 odd sort of school events, really, and we always try to do it. However, there's a limit to what we can do, and we, you know, like I said, this isn't our sort of full-time thing. It's very much something that just has to fit in on the sides. So doing work in schools has always been a big thing for us. Doing work in exhibitions is another big thing that we do as well. So we've developed some quite large-scale exhibitions. Sports Lab has been our project that we've been doing this year. It's just closed in Sheffield. It's been open in Sheffield for pretty much all of 2011, and it's had about 150,000 visitors. It's basically a hands-on, interactive sort of exhibition about sort of the physics and technology of sport, and that's moving to the V&A Museum of Childhood in Bethnal Green from March. I think the 31st of March it's opening. So that'll be a great show. Lots of sort of objects and interactives and sort of interesting stories, very much similar to what I've just been saying. We're also developing another sort of set of kind of the physics of sport kind of interactives for Intech, who are based near Winchester, sort of a science adventure centre there, and they're launching their new set of sort of sports science things in March as well. So there's quite a lot of that stuff going on. Great, absolutely fantastic for visits. Go in and really sort of get that hands-on feel for what's going on. We've also done lots of old ones. We were in Beijing, did a really big project called Velocity 2008, a really big sort of hands-on show, and we've also done stuff about horse racing. We've worked at Bristol, with the Singapore Science Museum, and the London Science Museum in the past. So that's been a really great way of trying to get this sort of topic out. It's been really, really successful and enjoyable, that. We do a lot of work with teachers as well, again, as much as I can. So do a lot of work with the sort of National Science Learning Centre and the regional science learning centres. I think I've got doing about 3 courses, I think, this spring, I think, in different places. We try and get out and sort of help teachers, sort of encourage them to just, you know, I guess it's all about trying to really get teachers really excited about their subject. I think that's what it's about, really, and sort of, you know, just sharing some interesting developments in contemporary science. We work a lot with the Youth Sport Trust. I'm going to their conference in a couple of weeks. We do a lot with our Centre for Science Education, but obviously here. We do a lot of projects with them around curriculum development. We've obviously worked with Nuffield in the past as well, and the Wellcome Trust. So I'll talk about In the Zone in a second. We do a lot of public events as well. So when we talk about public engagement, I think it used to be, generally in public engagement, it used to be this idea of this, you used to call it the deficit model. You know, I know all this stuff, about my subject. You don't know an awful lot. I'm going to stand here and talk to you about it. It's kind of what I've been doing today, really. But there's really been a move away from that and a move towards a much more of a dialogue type discourse where we've been doing a lot of this. So rather than, say, just doing stuff in schools, doing real sort of public events where we're really interested in hearing people's hopes and fears and using them to actually shape policy and to sort of almost to change what we're doing and where we're going to put our ideas and our money. And we've been doing that with, for instance, people with the Research Councils UK. Okay, so all the different research councils, this is where your taxpayers' money to fund research. They're hosting a series of debates this year about the relationship between science and sport. So we're hosting 6 major events. The first one starting at the Royal Institution, 25th of January, I think it's going to be. It's all about basketball. So we're doing 6 big events. They'll be fantastic, really big events. We've got top sports people to each one and top scientists, and we're going to be discussing these issues. And ultimately, that's about a genuine dialogue. And we're doing some research off the back of that, and that will then shape and inform, I guess, future funding decisions about where the research councils might invest their money. So that's a sort of a genuine piece of dialogue, really. And we've done lots of other things. We've done the Battle of Ideas. We've done always doing Café Scientifique type things, public forums where we can sort of share and hear these sound bites, and science festivals galore. So lots of stuff, an awful lot of stuff going on for us. And quite interestingly, I think this is something else I'll just sort of finish up on, really, is something that I've been doing recently in the last 2 years, is actually working with artists. So I hate this idea that as scientists are sort of culturally devoid. I'm fascinated by the world of art. I absolutely adore it. And I hate this the way we're sort of put in silos, that sort of scientists can't do art and artists know nothing about scientists, we can't communicate at all. We could have pulled together with funding from LOCOG, the sort of London Organising Committee. We got a great project together for the Cultural Olympiad. We called it Extraordinary Moves. And really, it's about there's lots of different. We've got loads of artists on board, but essentially they're creating lots of different sort of, I guess you might call it artistic interventions. You know, new work, new photography, new installations, new sculpture, new plays, new dance, all sorts of different art forms, but all reflecting on this notion of human enhancement and how we use technology to enhance our so-called natural abilities and how that might change and the issues of the ethics around that. I think it's been a really fascinating project. So loads going on there. We've got loads of different artists involved, so I can't really show all of them. But I mean, Jason Minsky is a leading contemporary artist. He's got a show opening in Sheffield. Does some really interesting work. And we've got a major new play opening at the Crucible in May called Leaner, Faster, Stronger, which is all about this, which will be great as well. So some really interesting stuff happening, actually. I guess it's all been made possible. Well, I hope we would have done some of it if it wasn't for the Olympics. But I think the Olympics has definitely helped as like a real galvanising force that has allowed us to do a lot of this stuff. So I'm going to... I forgot about this. Finally, how would you... Schools doing it for themselves, okay? What are the options? Well, there's a lot out there, really. I guess my message here is that a lot of people have got a passion for sport. It's pretty easy to think about whatever context you might be teaching in your school. Can I put this in a different context? And is there an interesting context that maybe I can use from the world of sport, something that I'm really passionate about? If you're passionate about football, you can talk about all sorts of things, forces and motion and all sorts of things, projectile motion, Newton's laws, loads of different things you can talk about. And if you do that, I think it really... your enthusiasm for it, I think, kind of comes across and gets transmitted to the people you're working with. And I think that's a really, really good tool. So there are, things you can dip into, like the stuff that we do and others are doing. But I really think that the best way is for those individuals in schools who've got a passion and can take it just to pick up and run with it themselves, really. There are things to help, of course. I guess the two big things I'll flag up here is the In the Zone project, which got launched yesterday with Steve Redgrave. Again, something we've been very involved in that from the outset. So that's a fantastic set of resources that are going around to every school in the country, if they so wish. less on the physics, more on the physiology side of things. But some fun, really well-developed set of curriculum resources and a great box with some quite significant bits of experimental apparatus to get your teeth into there. Really nice project, that. If for those of you who might be more interested in more of the physics side of things, I guess what I've been talking about, we have a blog called engineeringsport.co.uk where we have every week we put up a new article about something. How far could Usain Bolt jump in a long jump or something, Basically the physics of sport, unpicking it, and in each one of them, and there's hundreds of posts like that up there now that we all the whole centre contributes to. Could be a really nice resource for you to dip into and sort of take it on for yourself. So I think I'm going to leave it there. Sorry, I've gone a bit long, but I'd be more than welcome to take any questions after as well.